Good day. Today we will be talking about op-amps. Alright? Op-amps or operational amplifiers were first used in the early 20th century and were very useful because they are amplifiers, yes, but they can also do mathematical operations. Alright? What is an amplifier first and foremost? An amplifier is something that takes an input, multiplies it by a certain gain, and out comes an output. Right? In order to get the output, we multiply the input by the gain. Alright. So an operational amplifier works the same. It takes an input, multiplies it by some gain, and then we have the output. But instead of it being finite only, instead of it having only one terminal, it has two. There. So this is the positive or the non-inverting input. This is the negative or the non-inverting, the inverting input. And the input, the overall input is V plus minus V minus. Right? And it is denoted by plus and minus, so you know which one to subtract. And V out is V in multiplied by the gain of the operational amplifier. Alright. So, the unique thing about an operational amplifier is its gain. What is its gain? Maybe it's 1, maybe it's very high. It is indeed very high in the fact that in theory, the gain of an operational amplifier is infinite. This means that whatever the input is, we multiply that by infinity. So 2 volts being the input, meaning that the output is an infinite, positive infinity volts. Negative 1 volt of input in here means that the voltage, it means that the output voltage is negative infinity. Right? But you may ask, if the voltage is infinite, isn't it not realistic? Or at least, why are we studying infinite gain in theory, right? In practice, we actually have something called supply rails. Right, so it's now 5 terminals instead of 3, right? So this is positive VCC and negative VCC, and this is the limits as to where the operational amplifier's voltage can lie at, right? So 0 is in the middle, positive VCC and negative VCC. There we go. If the voltage exceeds positive VCC, that gets cut off and clamped down to VCC. And if the voltage exceeds negative VCC like that, it gets clamped up and it goes to negative VCC instead. Alright. So, if the gain is infinite, where can we make use of this? The only use for it without any kind of modification here is in comparators. Alright? So, if we have, say, this configuration, right? Say this is V plus and V minus. If we want to know which one of V plus and V minus is bigger, we simply need to know the input here, right? So, the differential input is V plus minus V minus, right? So, for example, this is 2 volts. This is 1.9 volts. Just as an example. The differential input is just subtracting this, so this is 0.1 volts. Right? What is the output then? The output is just it multiplied by infinity. So it's gonna be, since this is positive, positive infinity. And since it is positive, we are for certain, we know for certain that the voltage that is bigger is from the positive end or the non-inverting input. And it is 2 because 2 is greater than 1.9 volts. And in reality, if we were to use the VCC and negative VCC supply rails from earlier, this would not be positive infinity. This would just be positive VCC, which makes it more practical, right? So we can use this as a comparator, but that's the only use case for this configuration. So let's try to have another configuration, because we want the operational amplifier at the output to not be infinite. We want it to be finite, right? In theory. Okay? So how can we make it finite? What if we have an operational amplifier, right? And since this is giving us trouble, the differential input, what if we just connect the output to one of the inputs? Now that would be something, right? So let's connect it to some attenuation, right? Let this attenuation be alpha, where alpha is greater than 0 but less than or equal to 1. Alright? This is an amplifier. The reason why alpha is less than or equal to 1 is because, well, if you want it to be greater than 1, we need it to be an amplifier, right? And that would be kind of useless. Alright? So, what would we need? What would the output be? Let's write V in for the input and V out for the output. To not make this confusing, let's put V in D for differential input. Right? We have here just input and we have here differential input. Alright. We have differential input V plus minus V minus. So what is V plus? So V in D. What is V plus here? It's V in. What is the V minus here? That is alpha times V out. So this is an amplifier as well. Alright, minus alpha times V out. Right? And then to get the output, we just multiply it by the gain. Right? The gain A. Alright, so we get V out equals A V in minus A alpha V out. Alright. So now that we have this equation, we can solve for V out to get just the output. Right? So, V out plus A alpha V out equals A V input. Alright. So in here we can factorize V out of both terms. So we get V out times 1 plus A alpha equals A V in. Let's isolate V out by dividing by this. So V out equals A over 1 plus A alpha V in. Right. So let's erase this part. Right? So how do we solve this? We know that A is infinite. So how can we find for divide this? Well, we find the limit, right? The limit as A goes to infinity of A over 1 plus A alpha. What we can do is divide by A. Right? A divided by A is just 1. Divided by 1 over A plus A over A is just 1 times alpha is alpha. The limit as A goes to infinity of 1 over A is 0. So this would be 1 over alpha. So A over 1 plus A alpha is just 1 over alpha. And since since alpha is greater than 0, that means 1 over alpha is a finite value. It is only infinite if it is 0 positive, right? If it is equal to 0, which we don't want because that's undefined. So now that we have a proof that using this configuration actually makes the value of the output finite, which is good, we can use this in order to configure all sorts of amplifiers. Let's start off with copying. Let me just erase this. Let's start off by copying this circuit again. There we go. But this time, just removing this alpha, right? So now, since there is no alpha in here, and the formula, remember, was V out equals 1 over alpha V in. Since alpha is just 1, because this is shorted, we can say that the output is 1 over 1 V in, or just V in. This is what's called a voltage follower. Because whatever the voltage of the input, output follows, right? Now, why would this be useful? Because V out equals V in, that can also be achieved by just shorting the entire thing, right? So why do we need this configuration? Well, there is a reason for it, and the reason is because the input impedance of the operational amplifier is actually ideally infinite. So when we have an operational amplifier, right, we expect the inputs to be connected by some resistance or impedance, right? Because the internals of it is just transistors and a bunch of amplifier circuits using transistors. But ideally, this is an open circuit, which means by doing this, the input is disconnected from the output. So that would mean that without the op-amp, if the input is disconnected from the output, that would mean the output has 0 volts. But in here, since there is an op-amp, the output is now equal to the input voltage. So that's cool. There is voltage, but there is no connection. That's what a voltage follower is used for. Now, let's use this again, but this time let's put something that attenuates. What circuit can we use that attenuates the voltage towards the feedback? Now, what is the voltage divider law, right? When we have two voltages, they share the source voltage, right? There is a source voltage here, and then they share that between themselves. All right. So if this is R, let's say F, and then R, G. Sorry. Yeah, that's right. That's okay. The voltage across RG this is V in, for example, and maybe this is V out. V out is equal to V in, or whatever this is, times, wrong. That's correct. V out equal, it was just confusing, so let's just say this is VG, alright? To not confuse, and this is just V. VG is V times, we first divide by the total resistances in here to find the current. So RF plus RG. We multiply by RG in order to find the voltage there, RG. And that is the and that is the voltage. As we can see here, this is just a constant depending on the resistances. It could be a sort of attenuation or gain. If we look at here, RG and are both on the numerator and the denominator, and since RF is a positive value, this means that this is less than 1, which is befitting of alpha here. So we can use that in order to attenuate the voltage here. Right? There we go. And there we go. Let's do this as RF, this is RG. The voltage here is voltage out, and there's ground here. In here, this one. Alright, so let's just, we already know that. Alright, so we know the attenuation factor, which is RG over RF plus RG. So let's just put the alpha here as a known value now. RG over RF plus RG. And we know the output voltage of this configuration to be 1 over alpha V in. Right? So V out is 1 over alpha V in. Alpha is this, so let's just reciprocate that. We get RF plus RG over RG V in. Alright? Let's simplify because RG over RG is just 1. So we get 1 plus RF over RG, don't forget the parentheses, Vn. Right? This is the gain of this amplifier. Alright? 1 plus RF over RG is the gain. That means we can control the RF, we can control RF and RG, therefore we can control this gain. So by just adjusting RF, we can have whatever gain we want using the operational amplifier. This is a non-inverting amplifier. Right? Because it doesn't invert, the gain is positive. So that's good and all, but this is usually the second amplifier that we learn about in college. So I think you know, if you know operational amplifiers, you already know of the amplifier, right? The configuration that I'm not talking about yet. But let's talk about that. Because the negative feedback here that we have set up, actually it has a really great consequence. Because V out equals 1 over alpha V in, alright, where alpha is this value, this means this is finite, right? This means that output is actually finite. Remember the formula for V out earlier. It is A V in. Let's get input. So V in or V in differential equals V out over A. V out is a finite number. Our gain theoretically is infinity. This is 0. So the differential input between the input and the feedback is 0. Right? As a consequence of V out being finite. So the good consequence of this means that V in and V out have the same feed. This terminal and this terminal, if it is negative feedback, have the same voltage. This also has a voltage equivalent to V in. Alright? This is what's known as a virtual short. Why? Because this looks like a short, right? Because they have the same voltage. That is usually a short circuit. But remember, it has an infinite input impedance, meaning that it is not connected at all. That's why it's a virtual short. It's not connected, but it looks like a short. And if this is negative feedback, we can always assume that the input voltage across the non-negative or the non-inverting side is equal to the inverting side. So if this is 5 volts, we can already assume, since this is negative feedback, that whatever is in here is also 5 volts. And so since this is connected to here, this is 5 volts. So there we go. How can we use that to our advantage? Let me introduce to you the other type of amplifier. Right? If we have the non-inverting amplifier, let's have the inverting amplifier. Now, let's say we have, let's flip the, let's now flip it so we can draw it easily. There we go. Let's connect this to ground. All right, something that we have not done earlier, since we usually have the input as from the positive, right? Let's connect the input to the negative or the inverting. But let's connect a resistor here. And then let's connect a resistor across here. And this is the output. So now this is the feedback. This is feedback resistor RF. This is Rin, or the input resistor. Now, what would the voltage on the output be? What would the voltage be? Well, let's try finding the current. Alright? One thing to note that is in here, it's called V1. What would the voltage there be? Since this is a negative feedback loop, we can tell it's negative feedback because the output and the input is somehow connected to each other. Right? So this is negative feedback. And the positive is connected to ground. Usually ground is 0 volts. That means we can set V1 as 0 volts. There we go. So how can we use that to our advantage? We'll use resistance. Okay. What would the current going through Rin be? Well, that would be Vin minus V1 over Rin. What would the current going through RF be? Well, there is a branch in going here. But remember, the op-amp has an infinite input impedance. And if there is an infinite input impedance in there, this means that this branch is not connected to anything. Alright? It's not connected to here. So because it's infinite, right? That means there is no current going to inside the op-amp on the input side. Neither is here. There is no current going towards that. Only voltage is the thing we look at, not the current. Alright? So we can assume that all the current goes through the top, or RF. Right? So the current going here, and since there's no current going here, Kirchhoff's current law says that all the current must go to there. So the current going here and the current going here, same thing. Alright? So let's start calculating it. It's V1 minus V out over RF. And again, V1 is 0, so just remove that. There we go. We need the output, so let's just get everything on the other side. V out is equal to negative RF over Rin V in. And there we go. That is the inverting amplifier. It is inverting because there's the negative sign. So you might think that we use the non-inverting one, right? The one whose V out is 1 plus RF over RG V in. You think we might use this instead because of the negative. But there is a problem with this formula, it's the 1. That's tricky because we want to control the voltages, right? If we want, like, I don't know, 20 gain, we need to set up 19 gain here, and that's not that easy. But in here, we can set negative 20 gain. So that's still 20 gain. How do we overcome that negative, the inversion? Well, we have another stage, right? Where the gain is now negative 1. Negative 20 times negative 1 is positive 20. That is the same, right? So most of the time, we just use the inverting amplifier for analog amplification. All right. All right. Now that we have the amplification all good, let's have fun with amplification, right? Because who doesn't like fun, right? So we're going to be using the inverting amplifier for the next 2 bits of amplification. Remember, the output is equal to negative RF over Rin, it's gain, and then Bin. Alright. So now, what can we do here? Indeed, what can we do? Well, what if, let's just remove in here. What if we replace this one with a capacitor? Like that. This is spicy. Let's say this has capacitance C. Right? Let's say this is AC. In AC, instead of resistance, we have impedance. Alright? Still ohms, still the same thing. Impedance and resistance is almost the same thing with the addition of capacitive inductance and capacitive reactance, and also reactive inductance. So, what is ZF and Zin? Zin is just R, so that's a given. What we need is ZF. What is ZF? That is the impedance in between here. And from circuits to AC analysis, we know that this is 1 over J 2 pi F C. Right? There's a long story about why this is the capacitance. Right? But I don't have enough time to get into that. So this is what we have. Right? 2 pi F. All right. So from our from Laplace transforms, right? If you remember Laplace transforms, S equals sigma plus j omega. This will come in handy later. Let's just put that there. Right? 2 pi f. 2 pi f is something called the radiant frequency. Right? Where can we find 2 pi f? Well, when we describe a sinusoid, for example, Vp cosine 2 pi ft, usually have the coefficient of the independent variable t, time, as 2 pi f. This is radiant frequency. F is by itself is just the frequency. 2 pi f is the radiant frequency. 2 pi is because of the unit circle, right? Or because cosine repeats every 2 pi, and sine repeats every 2 pi. So 2 pi is what we call the period, or the radian period. We multiply it by frequency in order to get the radian frequency times time. That becomes the input for this one. Alright? We usually shorten it to omega. Remember? Alright? So 1 over j omega c. What else can we use here? J omega. There's j omega here. So let's just, I don't know, let's just put s instead, so it's easier to write. And there's also a reason for that. Let's just set the sigma to 0. Right? Setting the sigma to 0 it now becomes j omega. Right? That is frequency. Alright? In a future video, I'll tell you what sigma is about. But in short terms, this is about the decay or growth of a sinusoid. J omega is the frequency, as we have discussed. So let's just put j omega as s. Alright? So now, what is the gain? ZF is 1 over SC over Z in, which is R. The consequence of putting it in S is now that this is now in the frequency domain, or the complex frequency domain as described by the Laplace transform. Let's simplify it a bit, algebra. So this is going to be negative 1 over RC 1 over S Vn of S, because this is a function. This is also a function of S. 1 over S Vn of S. That sounds an awful like an integration. Alright? So, going to the time domain, V out of t now becomes it's a negative 1 over RC. Integral from 0 to t, that is the input t, V in of dummy variable tau d tau. So, just adding a capacitor in here, we have an integrator. Alright? This is what's called an op-amp integrator. And it's amazing how an op-amp, of all things, can integrate. Alright? Just using a lot of mathematical mumbo-jumbo. And that's why engineering and math is very intertwined with each other. You can do integration with just a resistor, capacitor, and an op-amp, which is just a bunch of transistors. Isn't that crazy? So if we can do an integrator, can we do a differentiator? We can. Can we do a differentiator, and how? Let's just swap this. Let's just swap. Alright, swap. Now, ZF is now R. Z in is, again, 1 over SC. This is our R. So, negative R over 1 over SC, V in, that's V out. Alright, so this can go up, up, negative RC, S V in of S. S times V in of S, that sounds like a derivative in the time domain, right? So V out of T equals, alright, let me go down for a moment, this is getting hard to write. Negative RC D over D tau, W variable, V in tau at tau equals T. And there we go. So again, just a capacitor and a resistor, we can already differentiate a function. Right? So whatever the input is in here, we can differentiate that, and that's really cool, right? So, but wait a minute. This is only meant for AC, right? Alternating current, or just a sinusoid. And alternating current, if I remember correctly, is very strict about what it can be for the input, right? Because we have a capacitor and we had the impedance of that capacitor. Well, that's why we changed the J omega for S. It's because we can now figure out the cases for which it has decay, which is some of the cases for sinusoid, right? That will be in a future video, the Laplace transform and why S is the way that it is. So, very good. We have an amplifier that can do mathematical operations like integration and differentiation. It can also do subtraction, addition, using the this configuration again. But that's for another time. Alright. Let's now go back to the real world. Alright. So let's talk about how an actual op amp will behave. An actual op amp does not have infinite gain. Usually op amps only have a gain of up to 10 to the power of 5 or 100,000. So that's still a lot. Alright? If you had like a 1 volt if you had like 1 volt of differential input, that would mean 100 kilovolts of differential output. That's why we have the supply rails. Alright? Because where else would the op amp get its power from? So that's why we have supply rails. This powers the op amp. So if it wants to go to if it wants to go to like 100,000, it only goes to like 15 volts or VCC. Let's set VCC and negative VCC to 15 volts. This is what I saw in a book. Let's set this to like 2 volts, 1 volt maybe. Right? So differential input is 1 volt. So the output is 100,000 times 1 volt. So that is 100 kilovolts. But it is limited by the 15 volt saturation range. So the saturation means that only has up to 15 volts. So there we go. And if this is switched, for example, this would be 1 volt, this is 2 volts. So 1 minus 2 is negative 1. It would go to negative 100 kilovolts. But since it is limited to negative 15 volts, it only stays up to negative 15 volts. And due to the nature of semiconductors, in that it has like the 0.7 volt barrier potential for like the inside transistors or whatever, the diodes maybe. This means that the output can only be 14.3 volts, but we don't talk about that. We just don't talk about that. Right, let's just talk about this. Right. So first, we are going to discuss common mode rejection ratio. Common mode rejection ratio. What is the common mode? What we have talked so far is the differential mode. Alright? So the differential mode takes the difference, multiplies it to the gain, and that's what comes out. The common mode is what happens when we connect them together. Alright? So when we connect both the inputs to one output, that is common mode. Alright? Where is this useful, right? Like if you connect them to that one, obviously there is no like there's no like voltage, right? Because 1 minus 1 is 0. 0 times whatever that is 0, right? This is again theoretical. We're now talking about the practical considerations of operational amplifiers. The common mode rejection ratio does not exist for like 1 volt. It actually exists because of one thing: noise. Right? Noise is uncorrelated. What that means is if we have one sine wave, right? The noise rides along it. If we have the inverse of that, the noise also similarly just rides on it. But if we had a device that can subtract the positive sine wave and the negative sine wave, so this is V plus negative, so V and negative V, right? If we can subtract these two somehow, so that is V minus negative V, we would get 2V. we will get twice the voltage. But, and the good thing about, and the positive part about this, and the reason why CMR is very important, is noise is uncorrelated. This is correlated to this one, right? By a lot actually, because it's just the negative of that one, right? This depends on this. The noise that inputs in here and the noise that inputs in here is not related at all. They may as well have the same polarity. If they have the same polarity, so let's put noise as Vn. That means that it doesn't have negative minus Vn here, it's just plus Vn. Right? If we then subtract these two together, we get 2V, but Vn minus Vn is 0. And that is the reason why we have differential input here. The noise cancels out on both sides. And how effective that noise is at being cancelled out is the common mode rejection ratio. Alright? CMRR is defined as the ratio between the differential mode, so that is usually the 10 to the 5, and the common mode ratio. This is usually 1 or anything lower than that. We do not want the common mode voltage, right? Because the common mode voltage is usually noise, which is uncorrelated. So the better this is, the better it is at filtering out noise because of the differential design here. So that's really cool. And if we want it to be decibels, make sure to have 20 because this is voltage. So 20 log CMRR, we get our dB of CMRR. Alright? Next. Let's talk about imperfections. So nothing is perfect. I think we all know that. Since nothing is perfect, if we just had like 0 volts here, so 0 volts means it's connected to ground. In a perfect world, this would not have any voltage. So this would be 0 volts as well, despite it having a gain of 100,000. Right? But this is not a perfect world. There is some leakage going from like positive maybe to negative, or maybe negative to positive. So we can model it by both still going through to ground, but there is now a voltage here. Alright, so there is some offset voltage here. Right? And this offset voltage is bad. Because if we had like ground, nothing happening yet, this would not be 0 volts, even though it's intended to be 0 volts. This would show negative 15 volts. And that's bad. If we want to do the operations, we need this to have no offset at all. Alright? That's why in ICs of operational amplifiers, alright, there are maybe the operational amplifiers like that. But there is this thing called an offset null. And that setting exists to null the offset of the op-amp. There is some offset in here. One of them is more voltaged than the other, or some voltage is leaking towards one terminal. That's the offset. We want it to null. So we want to adjust some parameter in here in order to match the voltage running across it, so that whatever operation you do, it's not affected. So offset null. Or maybe you can decrease the voltage across here by cancelling it out, or something like that. Offset null is something we adjust in order to have perfect operation. So that is offset. And for the last topic of the day, for op amps, is something called the slew rate. Right. An op amp has resistors. It also has transistors. It also has capacitors. This especially is very problematic because capacitors can charge up and charge down, or give its charge away, or whatever. Discharge, recharge, something like that. So that charge-discharge cycle takes time to go down, time to go up, and all of that. So inside the operational amplifier, there is a slew rate. This is the maximum rate of change in the waveform of either input or output. Right? So there is a maximum rate of change in either the input or the output. By rate of change, I think we all know what that is. That is the derivative. There must be a certain maximum value for the derivative. So how can we find that? Well, why did I say that either input or output? Because the output is usually way bigger, right? The reason I said that is if you connect it correctly, there is some configurations where they have like the input has greater magnitude, right? So let's not have input or output. Let's just have V. V has the highest amplitude sine wave of either of them, and let's just say this is a sine wave. And the one thing I know about sine waves is that the reason why in alternating current we only talk about sine waves and not square waves or whatever is because of Fourier transform. Since every signal is made off of sine waves, so we can just look at sine waves and not think about anything else. So here we go. So V of t, that is equal to Vp. This is the magnitude or the highest magnitude anywhere in here, right? Sine, so this is a bit easier to calculate. 2 pi f t. This is usually the form of a sinusoid from this is from circuits to AC circuits. We need the max rate of change, so we need rate of change, the derivative. So V prime of t is Vp. This becomes cosine 2 pi ft. Due to the chain rule, we need the derivative of 2 pi ft. The derivative of 2 pi ft with respect to t is just 2 pi f. So 2 pi f. Now we need the maximum. Right? Alright, so we need the maximum V prime of t. When can that be the maximum? Vp is not a variable, it's not a dependent variable. Neither is f. So this cosine 2 pi ft, since it has t, it is the only one with the only dependent on the independent variable t. When is cosine maximum? It's at 1. So this should be 1. So this is at Vp 2 pi f. Alright, so that's the maximum Vt. Right? And since the maximum Vt is the slew rate, this is now the slew rate. Alright? We got the frequency now. Right? So the frequency that we are allowed here is SR, slew rate, over 2 pi times Vp. This is the maximum frequency allowed for a certain slew rate and voltage, peak voltage from anywhere in here. Right? If it exceeds that, there will be attenuation that is unintended, or there will be distortion, which is again unintended. So we need to be below that. So that is slew rate. Alright? Slew rate, the unit of slew rate, the unit of slew rate is volts per second. Alright? But in higher frequencies, we're dealing with much lower lower time periods. So you also use microseconds. Be warned that when dealing with slew rate, we are usually talking about changes in microseconds. So in textbooks, we may see 2 volts per microsecond being the slew rate as the maximum. We need to have it SI. So we need to take into account the micro on the denominator. So it's now 2 times 10 to the 6 volts per second. Or 2 times 10 to the 6 volt hertz. Alright? And that usually works here because we have volt hertz here, volts here, so we divide the volts, we get the hertz. Right? So yeah, that is the magical world of operational amplifiers. I hope you learned a little bit about how op amps work. And this is just the start of a wonderful world. And yeah, thanks for watching.